Okay, so in this video we're going to be talking about resistance, how we go about measuring resistance, and how we can calculate the total resistance of a series of resistors. So let's first define what it is. So resistance is the potential difference across a component divided by the current through it. That's all resistance actually is in terms of its definition. So the symbol we use for it in equations is R, and the unit, we could measure it in volts per amp because it's potential difference divided by current, but that's given a name. It's called an ohm, named after the German scientist Ohm. So when we're talking about resistance in terms of describing what it really is, we're going to be talking about a few different things. So you should know already that to have a current passing through a circuit, you need a conductor. So we describe conductors and insulators using something called free electron density, or electrons per unit volume. So free electron density tells you how many free electrons there are in each meter cubed of a material that you think might be a conductor or an insulator. So metals tend to be our conductors, and they are conductors because they have a high number of free electrons per unit volume. So these are electrons that are not attached to atoms, they are actually free to move around inside the material. An insulator, conversely, is something that has a very low number of free electrons, maybe even none per unit volume, and that's why current is not able to pass through that material. So let's talk about what resistance is in terms of these charge carriers or these free electrons. So if you're going to be a conductor, you need free electrons, and to do that you need a kind of bonding called metallic bonding. So the size of the current that can flow through a material depends largely on its electron density. There's another factor we can talk about in a second. So if you have a high density, that means a high current can pass through. And that means the resistance is lower. So that's when you have in mind something allows a high current, it's going to have low resistance. So something else that could help with this as well. So if you have a large cross-sectional area, that also allows a high current to pass through because there are more charges available to carry the charge from one side to the other. So large cross-sectional area gives a high current, which means lower resistance. So that's resistance in terms of kind of charge carriers. There's another aspect to the resistance that we also need to consider, and it's in terms of collisions. I've put collisions in inverted commas because none of these particles actually collide with each other. They're all highly charged, so they're just going to repel each other and bounce off. They're never actually going to collide. So as charges, or the free electrons, move through a conductor, if we've produced free electrons, that must mean there are positive metal ions left somewhere else. And these are all locked together in what's called a lattice or a structure. So as the electrons interact with these metal ions, the metal ions will have the effect of slowing the progress of the free electrons, and the charges or free electrons will transfer some energy to the metal ions. And having obtained this energy, it'll be in a form of kinetic energy, they'll be vibrating. The ions will then transfer this energy to the surroundings as thermal energy. So resistance produces heat, essentially. So the way you can change this, so first of all, if you think about this, these collisions are slowing electrons down, that's going to be decreasing current. So these collisions are increasing resistance, if you like. But if you have a longer conductor, each free electron that passes through it is going to have more interactions with metal ions, and so you're going to get a lower current, which is again is going to mean a higher resistance. Okay. So how do we actually measure resistance? Well, there's actually no direct way of measuring it. So we've got a voltmeter to measure potential difference, we've got an ammeter to measure current, but you cannot directly measure resistance, even though your multimeter will have an option called an ohm meter on it. But I'm going to talk to you about what that multimeter is actually doing to give you a resistance reading. Okay, so first of all, you need a circuit in order to work out a component's resistance. So in terms of what you need a power source that's going to give you an EMF. You need the thing you want to find the resistance of with a voltmeter in parallel with it. So you can see that at the top. You need an ammeter to measure the current, and you need some method for varying the potential difference and the current. So we could have a variable power supply, or we can use a variable resistor or a rheostat. Okay, so this is kind of the circuit that you need, and this is the circuit inside your multimeter if it's measuring resistance. Alright, so we're going to talk about different types of resistance that we can get. But before we do that, we're going to define some terminology that we use. So there's a specific type of conductor or type of resistor called an ohmic conductor. And that's one in which the current is directly proportional to the potential difference. So we've used the term directly proportional in there. So let's define what that means as well. So directly proportional in terms of its specific mathematical definition says that if we've got a graph and we've got a line on the graph, if we pick a point on that line and we divide the y coordinate by the x coordinate, we should get the same value regardless of where we pick the point on the line. That's what mathematics says a direct proportional relationship is. What does that actually look like? Well, it looks like a straight line passing through the origin, and that's how usually we describe to someone what directly proportional means. But mathematically, that's often described as y equals mx, or occasionally y equals kx as well. There's a few different variations. So when you see it in the form y equals mx or y equals kx, the m or the k is referred to as the gradient or the slope of the line, and it tells you how steep the straight line is. Because if you think about it, you can have lots of different straight lines that go through the origin. Some are steeper than others, and this m or k value tells you how steep the line is. So let's have a look at this. So on the left, you can see we've got a directly proportional graph. It's a straight line through the origin. And we've picked 4 points on this line, labeled going from like x1, y1 to x4, y4. And what we should find is if we do y1 divided by x1, that should be the same as y2 over x2, etc., etc. And if k is the gradient of the graph, all of those divisions should be equal pretty much to that value of k. So that's directly proportional. We're also now going to describe inversely proportional, which is very similar to directly proportional with one change, so we have to be specific here. So if you have a graph that's inversely proportional, if you pick a point on that graph and multiply this time the x and the y coordinates, any point that we would pick on that line, that multiplication should come out as the same value. And in terms of what that looks like, so if you're looking at a graph, what you would see is x increases, y decreases, and you'd also see as x increases, the slope or the gradient of the graph decreases. But this description here describes a lot of different relationships: exponential decay, inverse square, lots of things. So this description is not enough to tell you it's an inversely proportional. We have to check the multiplication of the coordinates is a constant. So let's have a look at this graph. So this is or could be an inversely proportional graph, and I've picked 3 points on the graph, and if it is inversely proportional, what we should find is the product of the coordinates is equal to a constant value, which is why inversely proportional relationships are often described as being y equals k over x, which we could rearrange to xy equals k. Okay, so let's now go back to resistors. Now we've got those relationships. So one of them applies to an ohmic conductor. Remember, an ohmic conductor is directly proportional. So potential difference and current are directly proportional. So if we're doing an IV graph, or current against potential difference graph, it looks like this. So there'll be straight lines going through the origin. So remember that a component has low resistance if, for the same potential difference, the current is higher. So you can see on the right hand side, for the same potential differences, the currents are much higher, so we know that's a small resistance. And on the left, because we've got a large resistance, so for the same potential difference, we've actually got lower current. And for those of you interested, actually the gradient of this graph is the reciprocal of resistance. So if you found the gradient of the graph, did 1 divided by it, that would actually tell you what the resistance is. So that's an ohmic conductor. Let's now have a look at the IV graph for a filament bulb. So the IV graph looks like this. So a filament bulb is not an ohmic conductor because you can see it's not a straight line through the origin. As you move away from the origin, the gradient clearly decreases. Okay, so we'll look at explaining these graphs now. So in order to explain the filament bulb graph, we need to talk about the relationship of resistance with temperature. So the easiest way to show a relationship is a graph. So the blue line you can see here is what normal metals do. So you can see that the higher the temperature gets, the higher the resistance gets. And we'll talk about why that is in a second. And you can see if you take the blue line back to 0, which is the coldest possible temperature anything can be, the resistance generally doesn't become 0 for a metal. However, there are these other materials called superconductors, which if you get them cold enough, their resistance actually becomes 0, which theoretically means an infinite current can flow through them and that they never dissipate energy, which is kind of cool, but I'll leave you to investigate those on your own. We're going to talk about normal metals for now. So generally speaking, normal metals, as temperature increases, resistance increases. And the reason for that is the metal ions, which remember is what the electrons are interacting with as they go through the material. If they're higher temperature, they're going to have more kinetic energy. And what that's going to look like is they have a larger amplitude of vibration. And that's what causes the increased resistance. So how does that help us understand the filament bulb graph? Well, let's take a look at that again to remind ourselves what it looks like. So what's happening is the resistance is getting bigger as the current gets bigger. And the reason for that is because we're getting this effect we've just described. So with higher current, the charges are transferring more energy per second to the metal ions. Why? Because more charges are going through per second, so we're transferring more energy per second. So that's going to give the metal ions a higher amplitude of vibration, which you often describe as being high temperature. And that's going to mean the resistance of the component increases. So a higher resistance means a shallower gradient for an IG graph, because remember the gradient is equal to 1 over resistance. So bigger resistance, smaller gradient, which is what you can see happening here. As current increases, the gradient is decreasing here. And that finishes this video looking at potential difference, circuitry laws, and resistance. Alright, so the last thing we're going to look at for resistors is how to combine them together. And when I say combining, what I mean is find the total resistance of a combination or a set of connected resistors. So to be able to use these rules, you first have to identify series and parallel resistors, because those are the two types that we can deal with. So first of all, series will look something like this diagram here. They're connected end to end like this, so any charge has to go through all three of them. So to calculate the resistance of these, all we do is we add together their resistances, which is often expressed like this. So R subscript T stands for total resistance, and it doesn't matter how many resistors we have, we just add their resistors together. So what is the effect of that going to be? Well, the more resistors you add in series, the more the total circuit resistance is going to increase, which has the effect of decreasing the current passing through the resistances, or the current coming out of the battery. So that's series. And you might notice that this is the same thing, or the same effect, as increasing the length of the conductor. So I often relate the two in my head. Increasing length means more collisions for the free charges. Increasing the number of resistors in series also means more collisions for the free electrons. Okay. Alright, so let's now talk parallel resistors. So if we sketch parallel resistors, you can see the characteristic, remember, is that the charges should either go through 1, 2 or 3. That would mean they're in parallel, which you can see is what happens here. So we use a reciprocal rule to get the total resistance of parallel. What does that look like? This is what it looks like. So 1 over the total resistance is equal to 1 over R1 plus 1 over R2 plus 1 over R3 plus however many we've got collected in parallel. So it looks like this. So if we add more and more resistors in parallel, what happens is the current from the battery increases. Why? Well, we've got more pathways for the current to take here. So that has the effect of decreasing the total resistance of the circuit. So more resistance in parallel, decreased total resistance. Now you might notice this has the same effect as increasing the area of a conductor, and it is exactly the same. So increasing the area means there's more charges available to move the current from one side of a conductor to the other, and it's the same thing here. So in the previous video, I said that voltmeters have infinite resistance, and I said one of the reasons for that is it has no effect on the circuit resistance. So remember, voltmeters are connected in parallel. So if we imagine our R3 resistor here is actually a voltmeter, if we put R3 equals infinite into the expression, 1 divided by infinite is 0. If you're a mathematician and you disagree with that, feel free to not let me know that that's not quite true. I know that's right. It approaches 0. Maybe you prefer that. But essentially 1 over infinite approaches 0. So you can see it has no effect on the total resistance of the circuit. And that's one of the reasons we need voltmeters to have an infinite resistance. And that completes this video on resistors.